So in the chi-squared, the chapter 12, let's look at number 2. So chapter 12, number 2, and is there anything from chapter 4? Let's see. Number 8. Let's do those two. Or 8, maybe 8 and 9. Write that down. Okay. Okay, so unfortunately I can't make it any bigger, but it says perform a chi-squared independence test, provided conditions for using the test are met. A sociologist randomly selects 859 females, 15 to 19 years old, and asks to disclose her family structure at age 14, whether she has abused drugs. The following is a contingency table that summarizes the results. At the 5% significance level, do the data provide sufficient evidence to conclude that an association exists between family structure and drug history? So first we're going to decide what the hypotheses are. So for our null hypothesis for the chi-squared, it's always going to be that they are not associated, they're independent. Okay? So that would be this one. And then the alternative would be that they are. So either they're not associated or they're independent. That's the null. And then do they only give you one chance on those? Something like that. So maybe that's why there was a lot of partial credit. So we want to find the test statistic, and this is the number that's going to be our indicator of how much dependence there is between the two, at what level of dependence. So we know we're going to get that from StatCrunch. And we're going to choose these 4 variables. So we're going to do graph, stat tables, contingency with summary. And we want variables 2 through 5. And then the row label is variable 1. And we want the chi-squared test for independence. Okay, so we get a statistic of 5.88 with 3 degrees of freedom, because it's going to be 2 minus 1 times 4 minus 1, which would be 2 times 1 times 3, which is degrees of freedom is 3. So they want us to round to 3 decimal places. 5.880 is what I got. Okay, the critical value then is going to be for 3 degrees of freedom, chi-square at 0.05, 5% significance level, or 0.05. What is that number? And we got 7.815. Agree with what she's saying? Okay. Got it? Just remember, the higher the chi-squared statistic is, the more indication that what? That we have association or non-association? What's that? So they are associated, right? So we're going to compare 5.88 and 7.815. Do we reject or not reject, first of all? I'm hearing both now. So our statistic that's reflecting this data is 5.88, and our critical value for comparison is 7.815. Reject or not reject?
No, reject.
Do not reject. And then it says the data provides sufficient evidence of an association, or the data do not provide sufficient evidence of an association. Do not, right? Okay, and remember, so that came up like a week or so ago, that some people were writing, when you don't reject, they were saying there's no evidence, right? They're saying there's no evidence of an association. Well, that's not true, okay? This is, 5.88 is some degree of evidence of association. It's just at the 5% significance level, if we want to be right 95% of the time, it's not enough evidence, okay, to suggest that there is an association. Okay, so this, the statistic that we get is it's not one or it's not an all or nothing thing. It's an amount of degree, right? It's an amount of degree, and that's why we have to pick a significance level. And so, if we're going to say they're associated, we want to be right 95% of the time. That's what the 5% significance level means. So if we want to be sure we're right 95% of the time, this is not enough evidence to say that these are associated. We have to say it's it's possible that they are independent. Okay, questions on that one? Anybody? Okay, let's go back and look at a couple from the other one. So the last two, numbers 8 and 9. Okay, so we've got the following are age and price data for 8 randomly selected ambulances between 1 and 6 years old. X denotes age, Y denotes price. Use the information to complete A through F. So we want the regression equation, and we can do that through StatCrunch. So we're going to do stat regression, simple linear. X variable, X. Y variable, Y. Okay, and that gives it to us right there. $415 minus 24x, 2 decimal places. Okay, so it's giving us a plus sign, and it's an inverse relationship minus, so we've got to put the minus in there, minus 24. Does everyone catch that? I don't know, that might have been a cause of some difficulty. They're forcing it to be plus, and then if it's given as minus 24, then we have to put in negative 24. Plus negative makes minus. Okay, so we're going to graph it and see what it is. So since it's negative 24, we just know right away it's either B or D. Do you see that? So I'm going to just take a guess here that it's D. Good guess. Okay. Describe the apparent relationship Price remains constant as age increases. Price tends to decrease as age increases. There's no relationship. So as age increases, price tends to decrease, for sure. Okay, predictor and response variables. Remember, predictor is going to be our x, or independent quantity. Response is our y, or dependent. So age is predictor, and I forgot what it is. Price is response. Age, so A. Predictor variable is age, response variable is price. Outliers and potential influential observations. So remember, outliers are just, they don't fit the data set at all. It's maybe due to an error in collecting the data, or transitioning from the data to creating the table of values. And then potential influential observation is if you take it away, then everything would be very different. Okay, if you just took one away. So let's look at, so you might have discovered this, but actually you come over here. I wanted you to kind of graph it by hand, but it gives you the graph. So looking at our graph of the points here, any outliers or any ones that if you took it away would drastically change what that best fit line was. Doesn't look like it to me, right? So everything's pretty close. Okay, predict the value of the response variable for a 3-year-old ambulance. Okay, so now we're going to use our regression equation. And that's what this does. This gives us, if our age is 3, that's what x is, then the regression equation then would calculate what the expected price would be. So this is what, that'd be -72. So anyone got a calculator handy? 415.38 minus 72. 415.38 minus 72. Oh, the nearest dollar? Right. That's a cheap ambulance, right? 343, 38 what? It's the nearest 100. Okay, so the number that you get is 343.38. But this is hundreds of dollars, and they want you to round to the nearest 100. So 343,100, but then do you have to put it in as a... But then it wants it in dollars. Final check. Whew. Okay. Yeah, so it's kind of a little tricky there. You got to round. You have to round your values the nearest $100, but then they want it in dollars when you put in your answer in dollars. Okay, so I don't think so this is probably a very similar problem. But it's this last one where they don't form a linear trend. I'm guessing that's what happens on this last one. Okay. What do we say? Does it form a linear trend or not?
Yes.
You kinda. That's kind of hard to say what they're thinking about that. But yeah, it seems like when x is lower, we're getting an indication that y is lower. As x gets greater, y gets greater. So I think yes. That's what I would guess. But we'll talk about. So we see the difference between this regression fit and the last one we had, right? The last one we had was all the points are very close to the regression line. Here, none of them are very close, and so that's what we're going to talk about today. All right, so let's just see. We think there is. Okay, and there is. So then we find the regression line, and we can go from there. Okay, anybody have a question on the homework? Okay, so here's the plan. We're going to pretty much, so we got 4.3 and 4.4, coefficient of determination. So what is this about? So we're still talking about looking at two variables taken together and looking at the relationship between the two. So we've talked about linear regression, but here's a question that kind of brings up. What is the true predictor of the dependent variable? So remember, our dependent variable is our y-axis. And this is the response, right? And we're talking about this as a predictor, meaning knowing this value, it predicts the value of the other one, right? But we should really ask the question, is it truly predicting, or is the value of this first variable truly predicting what this will be, or is the best predictor of this just the mean of the data set? Because that's actually what we've been doing all semester. All semester we've been focusing in on what's the mean, and really just that one value, the mean, all semester long has been our predictor of the variable. So the mean of the response variable, so maybe in this, maybe it's right here, okay? So y bar. So it's this kind of question that we have. Is y bar the best predictor of what a data value will be, or what an outcome will be of this? Or is this other variable a predictor of what y bar will be? So then that's not a cut and dried question, right? So that's on a scale as well, as we've seen all semester. Okay, so it's not one or the other, but like in this example, it's kind of like, all right, we kind of see a trend there, an upward trend that possibly this, whatever this variable x is, it is predicting that the lower x is, the lower this one is. The higher x is, the higher this variable is. You know, but what if it was a bit more, this data was a bit more in a round cluster? Then maybe this really isn't predicting what this is, and just the mean of the y variable is the predictor of that. So does that scenario, kind of the question, make sense? What we're talking about? All right, so is x truly the predictor of y, or is just the mean of y the predictor of y? That's what we're asking. Okay. So looking at our regression line here, so here's a particular data point. Okay, here's a data point. Here's the regression line from all the data points. Okay, and then down here, say this is the mean of all of the output data points. Okay, so what happens is this amount of distance from the mean to the value of the regression line, that's deviation explained by the regression. Okay, and then the distance from the data point to the regression line, that's like error, right? That's not explained by the regression, because so the regression line is supposed to be a reflection of what the data is. So any distance that you have there, that's not coming from the regression, that's coming from error. Okay, and so then the total deviation is from the data point to the mean. Okay, but the distance that the regression line is away from the mean is a reflection of the regression, or reflection of the predictor determining what the response variable should be. But if this is the smaller this gets, the more that we see that, hey, look, the mean is just predicting what the outcome variables y are. But the farther this gets away, the more that the regression or the predictor variable is predicting what y is. Okay, so this right here gives us a value called SST, total variation in the observed values of the response variable. So this is kind of like standard deviation or variance. Okay, it's a number that reflects how far away our data values are in a cumulative effect of how far they are away from the mean. So this is similar to like standard deviation. And that's called SST. Okay, SSR, that is the variation in the observed values of the response variable explained by the regression. Okay, so that's this one right here, SSR. And then SSE is the variation in the observed values of the response not explained by the regression. So that's this one here. So what's the relationship between those three values? What's the relationship? Can you see from the graph? How could you make an equation of those three? What would it be? So you have the total amount of deviation from data points from the mean, which is made up of the amount of error from the data points to the regression, plus the amount of deviation explained by the regression. So what would that relationship between those be? She's saying the sum of SSE plus SSR equals SST. Ninos likes that. Do you see that? That's right. Because so it's this plus this is going to equal this. Or SST equals SSR plus SST. Okay, so make sure we need to understand what these things are. So make sure. Don't just wait for StatCrunch to get the numbers. You gotta know what this stuff means. Okay. So one more time. the more difference there is between the mean and the regression line means that that's indicating, that difference right there is indicating that, hey, look, the predictor is predicting what the outcome is. If these were real close, if the mean was real close to the regression line, it's like, okay, what's the point of the regression line, right? Just the mean is predicting. But the further that the mean is away from our regression line, it's the more that we see that there's deviation is explained by the regression, or that the response variable is responding strongly to the predictor. Okay? And so then the difference of the data point in the regression line then is not explained by the regression. It's just explained by spread of the data. Okay. So a strong indication of regression, or that this x variable is predicting the y variable, we see in the SSR being greater, right? The greater that SSR is, the more that regression line seems to be the real trend, instead of just the mean. Okay, and so then, that being said, we have this thing called the coefficient of determination. R squared is the proportion of the variance of the observed values of the response variable explained by the regression. That is, it's our SSR divided by SST. So now we're saying, what proportion is this deviation of the total? And that's what we just said. The more of this deviation that's due to the regression, okay, the more we're saying that x variable is predicting the y variable. And the less deviation, the less the deviation is as a proportion of the total, we're saying the less that it is, the more indication, and just the mean of the y variable is the indicator or predictor of the y's. And we already saw this. So this is our identity. It's called the regression identity. So this number, the bigger that proportion is, stronger indication that, yes, x is predicting y. And the closer that number is to 0, so this is a proportion, so it's going to be from 0 to 1. So the closer it is to 1, it means the deviation is explained more and more and more by the regression. X is predicting y. The closer it is to 0, that proportion, then we're saying that it's not. All the deviation is just how far the data point is from the mean, and so it's not about this predictor variable has less effect, and we could just predict y values by the mean of the y. Okay, so let's look at an example. Okay, so here's regression. So compute the three sum of the squares SST, SSR, SSE using the defining formulas. Okay, so we're just going to use StatCrunch to do it. I'll show you how this works. But you will have to know what those mean, okay? So we're going to go to, again, same thing as before. Go to stat, and we're still doing regression. Simple linear. It's just now that some of these, we're going to use some of these other numbers we didn't use before. So now if you come down here and you look at analysis of variance table for regression model. So here you see SS, sum of squares, SS, sum of squares. So here's SS total, 56. So what is that? That is the sum of squares of the difference between your data value and the mean of the data. Okay, so this has nothing to do with x, right? So this has nothing to do with the x variable. It's just the sum of the square. It's kind of like similar to standard deviation. It's just the sum of the squares from each of these from the mean of y. Okay, SSR. All right, that's our sum of squares due to regression. Okay, so look here, model. All right, the model, that's the regression line trying to fit the data. We're trying to model the data, so that's going to be 50. So that is our sum of squares due to modeling. So the higher that is in relation to the, so then the error, as sum of squares due to error, 6. Okay, then they want us to verify the identity. Does SST equal SSR plus SSE? Yes, 50 plus 6 equals 56. Okay, and then determine the value of R squared, the coefficient of determination. Again, that's given to us up here. R squared. And they want 4 decimal places. 0.8929. Okay, determine the percentage of variation in the observed values of the response variable that is explained by the regression. Well, that's exactly what this tells us, but we just need it as a percent now. So they want to round it to 2 decimal places. So 89% of the variation is due to the variation from the model, variation from the regression. So let's take a look at the graph. So here are the 3 values. So the mean, so maybe the mean is something like this. The mean of these is, or what is the mean? Let's see. Negative 10, negative 8. Negative 18 divided by 3 is negative 6. Right, so our mean is right here. Okay, and so you see, so it's like comparing, it's like look at this first data point. The total difference, like what's contributing to SST, is from there to there. Most of that is due to the regression, right? You see, most of that's due to the regression. So this is like this is what contributes to SST. This is what contributes to SSR. Okay, for this point, so from the data point, from the data point to the regression, let's see, from the data point to the mean is the SST. And then, so for this one, there's no contribution to SSR. But for this one, all of that is the contribution to SSR. And then point to the mean. So this is the SST. That's the SST. Right. So there's a negative going on here, right? So SST is a smaller value than SSR. Why? Because this is negative here. But the point is, this is very large, right? This is very large. The distance from the mean to the regression line is indicating a strong tendency towards regression. How useful the regression equation appears to be for making predictions. So that's what we're talking about. How useful? Very useful, not useful, moderately useful. What do you think? Yeah, because the 89% is so high, so much of the variation is due to the regression, variation from the mean, that yes. In other words, it's a very high indication that this x value is predicting y. Okay, doesn't make sense. Anybody have a question? Okay, so here's our ambulances. So we're going to analyze that ambulance situation again, but now in terms of this, looking at these variances. So we got stat regression, simple linear, x, y, okay, SST. Again, down here at the table at the bottom, here's our sum of squares, total of variance. So round to 2 decimal places, 0.88. 19096.88. Okay, SSR, due to the regression or due to the model, 18,007.5. Okay, and then due to the error, 1089.38. Okay, compute the coefficient of determination. That's our R square right here. 0.9, 4 decimal places, 0.9430. So that is giving us the percent. The percent of the variation of the observed values of the response variable explained by regression. So 94.30. So let's look at the graph and see if it's telling that story. Is age a predictor of the price of an ambulance? Or is it just kind of the mean of the price the best predictor of ambulance price? Is age a predictor of price, or is the mean price a predictor of price? Age. Absolutely age, right? I mean, look at this data. It's like so close to this line, right? So if the mean was something like maybe 310 or something, I'm just guessing. If that's the mean price, $310, certainly we would want to use age to predict price, not just the $310. Okay? And we're seeing because that trend is very strong downward, As ambulances get older, the price goes down. Let's see maybe if this other example is, do one more here. So this one is about, our bears, right? Chest size and weight. Distract us. Okay, let's do this one. So again, you're going to go stat, regression, simple linear, x, y, compute, SST, 7,489.5. SSR, 6393.59. Thank you. And then SSE, 1095.91. Okay, R squared, 0.8537. Okay, so let's just give you some credit for attendance here. So you're going to do the last two parts here on the sheet. Just you're going to write what the percentage is, and then what does that tell us? Impact ranges. But we still have more to do after this, okay? We're going to do the last section. So don't pack up your bags. So let's do this. Let's have you on your sheet. That's what you do. So number one will be interpret SST, SSR, and SSE with a sentence. So 3 sentences. Okay? And then 2, this is part C. So determine percentage of variation explained by the regression. Can you guys read that in the back? What this says right here? You can read it? Okay, good. So number 2 is going to be part C. And then number 3 is going to be to interpret that value. Okay? Go. Remember, I need name and date. Please work this way, up and down like this. That's a predictor. That's a predictor. Yes or no? Yeah, 85%. That's still pretty high. Now we see more kind of variation from the regression line that we did from the ambulances, but still very strong trend that this the bear chest size is indicating the bear weight or predicting it. Okay, can we go on? Any questions? All right. So let's talk about correlation. So correlation is just the next step of this. So this value R is called the linear correlation coefficient. Okay, and like before, we're going to use StatCrunch to find this number for us. So we're not concerned with all these scary symbols, okay? But anyway, so R is called the linear correlation coefficient. Okay, it's a number between -1 and 1. And it's an indicator of how strongly correlated our two variables are. How correlated is the X predictor to the Y response? But then we also see that there's negative in here too, so we want to talk about that. Okay, so let's take a look at this and try to figure out what's going on here. Here's R equals 1. This is R equals 1. This is R equals 0.9. Here's R equals 0.4. And then here's R equals -1. R equals -0.9. And then -0.4. Here's R equals 0. So observation, so looking at these data sets and then looking at these numbers. So what's an observation that you make about what this number is telling us? So anything. What's one thing that you see? Yeah. Okay, so the closer it is to 1, the more correlated the two variables are. And then, the closer it is to what, the less correlated? 0. So look at 0, right? So you can't really, there's no correlation here. X is not predicting Y. Rather, maybe the mean would be the best predictor we have of the Y variable is just the mean of Y. So the closer you are to 0, the less correlation you have. The further away from 0, or in other words, the closer you are to 1 or -1, the more stronger the correlation is between X and Y, or the more strongly X is predicting Y, right? The more strongly X is predicting Y. Another observation. So there's one more important observation to make here. Right, so if R is positive, what do you see? Increasing X indicates increasing Y. So these are directly correlated, right? So if X increases, Y increases when R is positive. When R is negative, when X increases, y decreases. Okay? Bless you. Okay. So there's the important distinction between correlation and causation. So this first one says, so do you see a correlation here between these two variables? Looking at these data points, what would you say? Would you say that R is positive or negative? Positive. Closer to 1 or closer to 0? Closer to 1. Okay, we got a pretty strong positive correlation. Now look at what the variables are. Ice cream sales and shark attacks. Okay? So, when people eat more ice cream, does that cause more shark attacks? No. Okay? So we have high correlation. But high correlation does not necessarily mean causation. Of course not, right? You know, the sharks don't have like the smell for ice cream blood or something, right? It's like, oh, they're eating more ice cream, so now they're gonna taste better to us or something like this. Why is this happening? Why is there a high correlation between ice cream sales and shark attacks? Okay. Okay, so what's the real cause of more shark attacks? Like what variable could we look at that's the real cause of more shark attacks? What's that? Okay, and then what's causing that? Summertime, which is what variable? Temperature, right? Temperature. So increase in temperature causes increase in ice cream sales. Increase in temperature causes shark attacks. So therefore, ice cream sales and shark attacks are correlated because this variable in the background, it's called a lurking variable of temperature, is what's causing both of these. But ice cream sales do not cause more shark attacks. So high correlation does not necessarily mean causation. Here's another one. Fresh lemons imported to USA from Mexico, decreasing. Total U.S. highway fatalities. Sorry, when there were more lemons imported, so when more and more lemons were imported from USA to Mexico, highway fatalities went down. Very strong. This is, here our squared number is 0.97. Take the square root of 0.97. Just do point, and that's our R value. Point what? Go ahead. Go ahead. 9.8. Very, very high correlation between lemon imports from Mexico and total U.S. highway fatalities. Okay? Is bringing more lemons to the U.S. causing fatalities to go down? No. This was actually just coincidental. Like they just happened to see that there was this increase. Over that time period, there was an increase in imports of lemons, and there was a decrease in highway fatalities. So this is just a kind of a coincidental correlation, okay? So you got to be careful. Correlation does not necessarily mean causation. But with more study, the point is that we are looking for causation, right? We are looking for, is one variable being predicted by the other? So we need more study, we need more research around a correlation to then determine or kind of deduce that yes, there is causation. Okay? But be careful, those are two different things. Right? So yes, when you have causation, you have correlation. But when you have correlation, you don't necessarily have causation. That's the point. Okay? So correlation is kind of our first step at trying to determine if there's causation or not. So you got to have correlation in order to say that this is the cause, but it's not guaranteed. You have to do more research, more looking into it to say that yes, there's causation. So here's two perfect examples of high correlation but no causation. Okay. So let's look at example. So that R value then, if you were wondering, so R, remember, is that percentage? Is that SSR over SST? And that is the same value R, our correlation coefficient. So if you had that number between -1 and 1 and you squared it, it would be that ratio we just talked about earlier in class. It'd be that ratio. Let's see if we can find one here. Look. I lost the textbook. All right, let's see here. Something different, hopefully. Okay, so here's following the agent price in hundreds for a certain type of car. Obtain linear correlation coefficient by reading the formula, interpret the value of R, and then determine the coefficient of determination by squaring R. So let's just run through this. So open a StatCrunch. We're going to do, again, still doing regression. Simple linear. X variables X. Y variables Y. So if you notice, we were looking at the R-squared variable, which was our SSR to SST ratio. But right above that is the R, the correlation coefficient. So 3 decimal places be -0.893. Okay? There is little or no linear association between the two variables. There's a strong negative linear association. There's a strong positive linear association. A, B, or C? B. Strong negative. Negative 0.89 is a strong negative linear association. Okay? R squared. So R squared is this ratio that we found before is this correlation coefficient squared. Okay, which we were pulling off here, but if you square that number right there, you will get that ratio that we computed before. 0.3 decimal places, 0.797. Let's look at the graph and see that strong negative correlation. So this is still, I think we had the highest one we had was the ambulances, and then next lower from that was the bears, the chest size and weight, and then this is still a little bit lower. It's still very strong, but it's lower because we see more deviation away from these points, away from the regression line. But still a strong linear, negative linear correlation at 0.893. negative 0.89. Okay, so the question is, does age cause price to go down? Well, just from the numbers, so just the numbers don't tell us that for sure, okay? This is only talking about correlation. We can conclude for sure that there's a strong correlation between age and price. In order to then show causation, we have to use other things. More data, more research, common sense, okay? Is this the thing that's predicting the price? Probably, right? Probably age is causing price to go down. But that's bringing in common sense. We'd have to do more research. So the numbers that we're crunching are only about establishing correlation and not causation. In this case, we could use our common sense and say, yeah, age, with age is the reason that the price of cars goes down. Okay, so what I'll do is this last homework will be due tomorrow night, Tuesday night, before class tomorrow, okay, not Sunday night. So I'll send an email out to remind you, and then we'll do review problems for the exam next week. We'll start those on Wednesday.